Hi, I'm Abu Bakr Dawood from Center for Advanced Robotics at Queen Mary University of London, and I'll be presenting our work, Silicone-based Capacitive E-skin for exteroception and proprioception. Scientific advancements have mostly been inspired from living organisms. Many developments in soft robotics are products of inspiration from soft-bodied organisms like octopus, jellyfish, and plant roots. Unlike soft robots, conventional or hard robots have extensively been used in industry. These conventional robots lack inherent compliance and are isolated from human workspaces. Soft robots, on the other hand, are made from soft materials, are compliant, and can easily be used in confined places with humans around them to ensure safe human-robot interaction. However, the compliance of soft robots and their infinite degrees of freedom make their control a challenging task. For a better control, a soft robot needs to have sense of its position, that is, its stretch and bending. Apart from its proprioception, a soft robot needs to be aware of its external stimuli, hence the exteroception as shown in this figure. Here are some of the basic sensing technologies that have been used for sensorizing soft robots. The most common are stretchable resistive sensors. Different approaches have been employed using the same sensing principle. Weidemann and others have used electroconductive yarn embedded into the soft robots for shape sensing. A sensory module for soft robots was developed by White et al. This sensory module was composed of resistive strain gauges. Microchannels were made in silicon substrates and were filled with gallium-indium alloy, a liquid metal at room temperature. Change in resistance for different stretches was measured, and this information was used to reconstruct the shape of the robot. Giffney et al. Devised a printing method for printing carbon nanotubes inside a silicon substrate. The sensor could withstand the stretching up to 300% and a maximum hysteresis of 11%. Kovico and others used screen printing methods to print silver conductors onto an elastomer substrate. These resistance-based sensors were characterized and were integrated onto a soft pneumatic actuator, resulting in curvature estimation. Optical methods such as optical fibers and optical waveguides have also been used to make reliable strain sensors. Ozil et al. Analyzed soft bending actuation modules integrated with commercially available resistive plex sensor and Hall sensor separately, and concluded that the magnetic sensor integrated actuation module showed more repeatability and precision as compared to resistive sensors. However, when magnetic sensors are used, the system needs to be isolated from the external magnetic fields. Shintake and others used carbon black filled elastomer to make a multi-layered strain sensor, having both resistive and capacitive elements. It was established that the performance of capacitive elements was superior to that of the resistive ones because of its high repeatability, low hysteresis, and high linearity. Now, we move on to the combination of different sensing technologies for measuring different stimuli. Mylino et al. Developed modular pressure sensors that can be embedded with curved surfaces and can measure pressure. Their approach utilizes non-deformable capacitors for correcting sensor variation due to temperature changes. Larson and others used Ecoflex-based sensors to measure change in capacitance with stretch, pneumatic pressure, and external force individually. However, the response because of two or more stimuli acting at the same time was overlooked. Totaro et al. Have made a proprioceptive and exteroceptive sensor by using two different sensing technologies in one sensor. Bending was sensed by the change in resistance of thin tracks of gold nanoparticles implanted by using supersonic cluster beam implantation, while external force was measured by change in infrared intensity within the sensor substrate as measured by phototransistor. This sensor has shown promising results. However, the integration of this sensor in a soft actuator, different deformations of soft waveguide depending upon different types of indenters, and the dependence of refraction of IR in different materials are yet to be studied in detail. A graphene-based e-skin to measure humidity and pressure was developed by Dong et al. In addition to this, the temperature was measured using the change in resistance of the graphene layer. However, detecting and decoupling different modes of mechanical stimuli such as pressure, force, and strain by utilizing a single sensing technology is an outstanding challenge in the domain of soft sensing and soft robotics. In this work, we develop a silicon-based capacitive e-skin for exteroception and proprioception that uses a matrix of capacitive sensors and propose a decoupling algorithm that can calculate the global strain and identify the location of a local indentation at the same time. Let's move on to methodology now. First of all, the mold for curing the silicone was designed on cryoparametric, and Ultimaker was used for 3D printing this mold. PLA was used for rapid prototyping the mold. Mold was designed in 4 parts. That means for curing successive layers. We used EcoFlex because of its low cost, ease of use, and its biocompatibility. The terminals for the e-skin were printed using conductive carbon grease. This carbon black grease is off the shelf and is highly stretchable. A stencil for making carbon grease terminals was also 3D printed. An interlocking design for making terminals was used, as this design is proved to have better sensitivity as compared to rectangular patterns. A copper tape of 0.7 millimeter thickness was used as a connection between carbon grease terminals and the external circuitry. This figure shows 4 steps for making e-skin. Figure A shows the cured base layer of EcoFlex. Figure B shows the first EcoFlex layer of interlocking carbon grease terminals and the copper tape connections, with 0.5 millimeter layer of EcoFlex cured on top of it. Figure C shows the second set of carbon grease terminals with a layer of EcoFlex cured on top of it as well. Figure D shows e-skin just before disassembling the mold. The final layer of carbon grease terminal was the ground layer, and it was made by combining first and second layers of carbon grease terminals. 4 copper tape terminals at the corners show external connections to the ground layer. For stretching the e-skin, an M8 lead screw with a Sunco stepper motor was used. The motor holder and the clamps for holding the skin were 3D printed. The clamps were designed to have cavities for the header pins to be connected to copper tape connectors. For measuring the capacitance, we used an integrated circuit CAV424 by Analog Microelectronics. This capacitance to voltage converter compares the capacitance that is to be measured with the reference capacitance and converts the difference into voltage. We used CAV424 with a couple of 16:1 multiplexers, one for X terminals and one for Y terminals. Figure shows the flowchart for data acquisition. The voltage from CAV424 was read by analog to digital converter of an Arduino, and it was serially sent to the computer. The second figure shows the complete experimental setup with clamped skin, stretching mechanism, and the circuitry. Now the decoupling algorithm. We have 20 terminals, 10 X terminals and 10 Y terminals. The data was collected in 2x10 matrix. Then the percentage change of each 2x10 matrix with zero state was calculated, and this 2 cross 10 data was then converted into 10 cross 10 matrix, giving us 100 nodes of the E-scan. From this 10 cross 10 matrix, peak value of the matrix was found, and this peak value was proportional to indentation. This peak value also gave us X and Y coordinates of the indentation. For calculating the stretch, we used a heuristic approach and defined 4 nodes along the diagonal. After finding the node of indentation, the distance of this node was calculated from 4 diagonal nodes. 2 diagonal nodes farthest from the node of indentation were selected, and these diagonal nodes gave us the corresponding terminals to be used for stretch calculation. By using the change in capacitance of these terminals from zero state and by using stretch calibration curve, we calculated stretch. The first figure shows the percentage change in capacitance of different X terminals with different stretches. Figure also shows the average change of all the X terminals. This average curve was used as stretch calibration curve in our algorithm. Next, two figures show two indentations at 5 mm and 10 mm at node 6, 6 when the applied or actual stretch was 1. Stretch axis of all these surface plots shows the calculated stretch from our algorithm. It can also be seen that the peak values are proportional to indentation. First two figures show 5 mm indentation at applied stretch of 1.124 and 1.2475 respectively. The calculated stretch can be seen on the stretch axis. Third figure shows the indentation at node 3, 8, while the applied stretch is 1, as shown on the stretch axis. Now here, first figure shows a true stretch versus calculated stretch. It is evident from this plot that irrespective of indentation, the algorithm calculated the stretch accurately. The second figure shows that as the indentation depth is increased, percentage change increases at a decreasing rate. We conclude that algorithm showed promising results. We were able to quantify indentation, localize it, and calculate the stretch. For the investigated cases, an error of 2.6% was found between actual and calculated stretch. Future works include the quantification of applied force instead of indentation, application of machine learning for decoupling these stimuli, and application of our soft capacitive E-skin around a soft actuator. Thank you very much.